So, in the last example, we looked at a sheet that's submerged, and we want to think of it as submerged as flat. And there's no need to use any calculus methods to find the total force exerted. But what if, on the other hand, we weren't submerged uh, with the plate sort of oriented horizontally, but the plate oriented vertically? Right? Then each step of the plate is at a different height. So how do we solve something like that? Well, so what we can do here is the same kind of approach we took when we were doing things like, computing work. Right? So if we have, say, a plate, this plate's going to be purple. Let's say we have some plate, right? And it doesn't have to be a rectangular shape. It can be any shape, as we'll talk about. And let's say it's submerged in some fluid here. I'm going to call this X and this Y here, right? Now, actually, normally what we'll want to do is, try and choose these axes in a convenient way. But I'm just going to put this here for now, right? And, well, again, when we're trying to do this kind of thing where, the whole thing is variable and we want to add up everything, we need to identify certain pieces of this. So here, we're going to say we want to pick the highest part and the lowest part, right? So the lowest part here will be C. The highest part we're going to call D. All right? And then what we're going to do is we want to find on, say, this piece, this little strip right here, right, of thickness delta Y, we want to find the force exerted on that part. Okay? And inside here, we're going to pick a point YI, of course, as usual. This is going to be sort of our sample that we're going to use. Right? How are we going to find the force on that? Right? Well, YI is going to be our depth of that part. And we can think of sort of that little piece of it. We can just apply that force, fluid force thing that we talked about in the last section. So on this part, we're going to say the force exerted is delta Fi, right? And it's going to be, the weight density of our fluid, whatever that happens to be, times the depth times the area of that. Okay? Now, regardless of what kind of shape we have here, we can always approximate this strip here as a rectangle. All right? Now, even if the overall shape isn't a rectangle, or say it's a trapezoid, we can always approximate each little strip as a rectangle. So what are we going to do here? Well, the weight density, again, that will just be dependent on whatever fluid we're submerging in. The depth here, the depth is actually going to be exactly this YI right here, right? So times YI. Sorry, I said that a bit wrong. It might not be that. This is going to depend on how we choose our coordinates. So let's say the depth, we can think of that as sort of the height of that specific piece. Let's call that h of yi. Okay, we're going to let h of y is going to stand for the depth. Right? And then here, we need something for the area. Well, area is length times width for a rectangle. And again, assuming this overall sheet, again, here I drew a rectangle, but assuming overall it's, the width of this will change as we go up or down. I'm going to let L of y, this is going to stand for the length. If I can spell. Length. Right, then the area will be the length of that specific piece times delta y. Okay? So this is the approximate force, right, on this strip right here. Okay, so of course then we want to add up all these forces. Not sure why. Oh no, that was right. So what do we want to do then? What we want to do is we want to add up all these forces, and so the total force will be the integral from C to D, right, from the very bottom to the very top of this, of W H of yi. Oh, sorry, no more i's here. So W times the height times the length, dy. Right? So again here, we're integrating with respect to y because we're thinking of this as submerged horizontally. Okay. So let's look at a specific example for this. Right? So let's say we have the typical example would be, say, a dam. Right? We're going to pretend that's a dam. And let's say the water level is right here. Right? And then in this dam, we have a door that's in the shape of a trapezoid. Like this. Okay. Let's mark some dimensions on this. Let's say the dimension from water level to the top is 4 feet. Okay. The width at the top of this is 8 feet. All right. The width at the bottom is going to be 6 feet. And the overall height of this thing is 5 feet. Okay. So given that information, we want to figure out the total fluid force exerted on one side of this dam, right? Of this dam gate right here. Okay. So how do we find the depth function here? Right. Let me keep drawing this down here. Okay. So in other words, where do we want to put our coordinate axes here? Well, the coordinate axes, one thing that's really going to be helpful is if we sort of take our y-axis to actually go right up the middle here. Okay. Sorry, this didn't say FT for feet. So we're going to take our y-axis to go right through the middle of this gate. This will make life a little bit easier. And we're going to take the x-axis to be right at water level. Now, what's the benefit of that? Well, the benefit of that here is if we measure from here to here, this is just x. Actually, I should use a different color if I'm going to do that. Right? From here to here, at any point, is just going to be x. And since this is a trapezoid here that's symmetric, if we find a function here, if we find the force on this part, we just double it and we get it on both sides here, which is quite convenient, actually. Okay. So, that'll help us find the length function. Now, another reason, the reason why we put the x-axis at the top of the water here is because now the depth function is just going to be a function of y. Right? Specifically, let's see here. The height function All right, so we want to say, if it's submerged 6 feet deep, we want the output of h to be 6. So, like, say here y would be -4. We want h to output +4 here, so we just call this -y, right? Down here at the bottom, we would want h to output 9, because it's 4 plus 5 feet. So that's y is -9 here. So we need it to, again, output 9. Right? So the interval for y, it's a good idea to maybe point out now, y is going to go from -9 to -4. Because that's 9 feet deep up to 4 feet. Okay. So now that we have this, we can start trying to figure out, all right, well, what's an equation for this edge of the trapezoid right here? So to do that, we want to give coordinates to these 2 points right here. Now, the nice thing is that's not actually going to be too bad, because we know that the whole width of the top is 8 feet. Since we drew y right down the middle, that means there's 4 feet on either side. So the x value here is 4. Right? We know the top of this is 4 feet deep, so this is 4, -4. That's the coordinate for the top right corner. We can make a similar argument for this bottom right corner to say that this is going to be 3 minus 9. All right? So once we have that, we can find an equation for this line right here. All right? So doing that, okay, so equation for right edge, right? We're connecting the point 3 minus 9 to 4 minus 4. So what we can do is say, all right, well, this is y minus -9 equals, we're gonna use point slope form here. We have -4 minus -9 over the change in x, so 4 minus 3 times x minus 3. Okay, so simplifying this, we have y plus 9 equals, this is going to be 5x minus 3, which ultimately will give us y equals, actually, yeah. Let's see. We actually need to solve this for x because we need a function of y. So let's multiply out this right-hand side. This is 5x minus 15. All right, so moving the 15 over, we have y plus 24 equals 5x. And so x equals y plus 24 over 5. Okay. Now again, remember here, that's this distance right here. X is this distance. Okay. So L of y, in this situation, if we want the total length of this trapezoid, we have the x from this side and the x from this side. So it's actually 2 times x. So 2x. So that means we get 2y plus 48 over 5. Right? Now that we have all our pieces, we get to put them all together. So the total force exerted on this is going to be the integral from -9 to -4 of the weight density. Again, we have here water, so this is 62.4 times the depth, so times -y, right? Something nice and simple here, times 2y plus 48 over 5 dy. Right? So now we would just have to compute whatever this happens to be. So I'll just go ahead and write the answer here. Again, I'm sure you all can compute something like this by now. So the answer here, once all is said and done, is this going to be 13,936 pounds of force. Right? So again, the actual computation isn't the most interesting part. It's really setting up the integral here. Right? So hopefully this concept here made sense, what's going on. And that's it.